So, thank you very much, and I really appreciate the possibility of presenting this research concerning the use of recycled CO2 in cement-based mortars. So, this is the outline of my presentation. I will start with the motivation of this work, so the significance. Then I will show you some tests performed on cement-based paste with CO2 with the aim of evaluating the maximum absorbing capacity of the paste, so of the cement and water. Then, when we have already defined the maximum capacity, we tested the cement-based mortars with the maximum CO2 that we can add to this cement-based system. And in this test, we measured the mechanical properties and the statistical analysis also on these on these properties. So, after conclusion, I will show you some idea for future works. So, we have a lot of CO2. They are obtained. This quantity is obtained from several chemical processes, and it is important to recover it, not only because CO2 is producing the greenhouse effect into the atmosphere, but also because in this way it is possible to create a new economy. So by producing and selling this CO2. When we add CO2 to a cement-based material, in practice we have the carbonation of calcium carbonation, like the carbonation of calcium hydroxide, as you can see in this picture. Well, there are three ways of carbonating the cement-based systems. The first one I reported here is the post-carbonation. So in practice, after casting, the concrete are introduced within a carbonation chamber. You can see here. In this chamber, you have the presence of CO2, and they remain here for some days, some hours. It depends also on the type of cement that you are going to use. This is the first approach. Another approach is the pre-carbonation. In practice, in this case, are used some calcium-rich minerals. Some of them could be slags from the production of steel, for instance. They are mixed in water and then are carbonated by adding CO2. This slurry is added to the ordinary components of a concrete system. So the third one is okay. Thank you. So the third one is the addition of CO2 into the mixture during the the preparation of the samples. For instance, here we have the normal situation, water and cement. After mixing water and cement, we can add solid and gas CO2 in forms of solid and gas, and so in this way we can obtain a new cement paste with nanoscale carbon tubes. So, remaining in this third approach, in which we have the addition of CO2 as a traditional additive, we would like to do something more by using CO2 with dry ice pellets. These are the pellets that we would like to use. The idea is to use these pellets in order to simplify the procedure of obtaining cement-based materials with the addition of CO2. The idea is that this addition can be also provided by unskilled workers. And we would like also to analyze the addition of CO2 in cement-based mortar, not only for concrete. Another goal that we would like to reach is the measure of other mechanical properties concerning the cement-based materials. And in particular, we would like to see the flexural strength, or what happens to flexural strength, not only to compressive strength. Finally, a statistical distribution of flexural strength and compressive strength is also investigated. So, to obtain the first goal, we performed a test on cement-based pastes. To achieve the other goals, we performed tests on mortars. So these are the dry ice pellets. So let's start with the test on paste. In practice, we used a paste with the water-cement ratio of 0.05. And the first three specimens were made with this water-cement ratio. The ratio you can see here, the quantity of cement and water. And we used three contents of CO2, 0, the reference cement paste, and then we used 1.6 and 3.2% of CO2 with respect to cement. We used these two content of CO2 because we found on the literature that the maximum absorption capacity of CEM1 cement, more or less, or something similar, is 1.5%, around 1.5, 1.6% of with respect to cement. So we used these three in order to see what happens also when we had more than 1.6% of CO2. Then we tested other two types of paste. In the first one, we added also an hardening accelerator. And in this case, we used 7 different additions of CO2. The last one is the use of an expansive agent to the same type of paste. And also in this case, we used 7 different additions of CO2. The idea was to try to increase the content of the CO2 absorbed by the system by using these additives. One of these additives is also based a calcium based agent. So after casting, we cast with this paste some cubes, and then we test after 28 days these cubes in compression. So you can see here the results, the compressive strength versus the content of CO2 with respect to cement. In the three systems, you can see you do not have a great difference of the compressive strength. It's more or less around 40 megapascal, and 42.5 megapascal is the strength of this type of cement. Moreover, we can say that the presence of additives does not modify the compressive strength remarkably. So, but our goal was not to change the strength, but to observe the quantity or the effect of CO2 by measuring the calcium carbonate that we obtain from the addition. As I showed you before, if we had CO2, we obtain the carbonation. So the results of CO2 should be an increment of calcium carbonate within the cement-based system. Here you have the way to measure the apparatus to measure the content of calcium carbonate in the cement pastes, and in this diagram you have the difference of the content of calcium carbonate with respect to the situation in which we didn't add any CO2. So starting from 0, you can see in the three systems we analyzed an increment, more or less an increment of the content of calcium carbonate up to 1.6%, around 1.6%, and then you have a decrement of the presence of the calcium carbonate. If you had, in this situation, about 3% or more than 3% of CO2, you have also a reduction of the content of calcium carbonate. This is probably due to the fact that we are adding to the system dry ice pellet, and these dry ice pellets are at a temperature around minus 60 Celsius degrees. So you have a reduction of the temperature within the concrete, within the cement paste system, and probably all the reaction that you are observing in absence of CO2 does not occur. So we, as a result, we obtain that the maximum capacity, the maximum content of CO2 that we can add to the concrete system is around 1.6% with respect to cement, and the addition of other components does not modify this absorption remarkably. So we performed tests on mortar considering 1.6% as the maximum content of CO2 that can be absorbed by the cement. And these mortars were obtained by following the European standards. In the European standard, to obtain only 3 specimens, like this one, the specimens were 40 by 40 by 160 millimeter, they are prisms. you use 1,350 kilograms of sand, 450 grams of cement, 225 grams of water. So as we would like to perform a statistical analysis for the ordinary mortar, we cast 30 specimens. So we multiply all these contents by 10. And so you can see here the contents, the components of the plain mortar obtained by following the European standards. Then we repeated this approach by adding 72 grams of CO2, which is 1.6% with respect to the content of cement. And as we observed before, the addition of other materials, of other components, does not modify the absorption capacity. We didn't use any additives. So following the European standards, with this specimen, we can have both the flexural strength, because we can test them in 3-point bending up to the failure, and so we can calculate the flexural strength. And after the flexural strength, the specimen is divided into 2 parts, and on both the parts we can also perform the compressive test. So with the same material and the same specimen, we can have both the flexural strength and the compressive strength as well. So here we have the results of this test. On this diagram, we have the probability density of the flexural strength in the mortar without any addition of CO2. On the right, we have the compressive strength, the probability density of the compressive strength for the same type of material without any addition of CO2. In the bottom part, we have the same diagram, flexural and compressive strengths for the same property, the probability density function. In the case, we added 1.6% of CO2 with respect to cement. So, as you can see, for flexural strength and also for compressive strength, the modal value remains the same, more or less the same. And as you can see in the next slide, also the average value of flexural strength and compressive strength is the same. However, as you can see, comparing the flexural strength without CO2 and with CO2, there is a different distribution of the strength with respect to the modal value in this case. As you can see, you have a reduction of dispersion when you add CO2 in the cement-based system. And this is this is true also for the compressive strength. So both flexural strength and compressive strength, the average value is not modified, but the distribution around the average value is different. So, if we summarize this test, the average value does not change. And here you have the average value of flexural strength with and without the addition. And of the compressive strength the same, is more or less the same. However, if you see the distribution, the standard deviation reduces in both the cases when we have the addition of CO2. And in particular, the reduction of the standard deviation is 22% for the flexural strength and 35% for the compressive strength. In other tests performed by other authors, this reduction was 25% if you consider the compression. So in this case, we can say that also for flexural strength, we have more or less the same reduction of standard deviation. Finally, to check whether or not two populations are similar, F-test is generally performed. And we performed this test for the two systems concerning the flexural strength and for the same system concerning the compressive strength. As you can see here, the F-test in the case of flexural strength is lower than the limit, and so we cannot say from a statistical point of view these are two different systems from concerning the flexural strength. But concerning the compressive strength, the F value is larger than the limit, so we have two different systems. So in this system, the standard deviation and the variation around the average value is completely different. We cannot reproduce the distribution of strength with the same variance in these two cases. So the addition of CO2 changed from a compressive strength point of view the systems. So to conclude, also cement-based mortars can absorb CO2 in form of dry ice pellets. So you can mix the traditional component, and after mixing, you can add these dry ice pellets. So the maximum absorption capacity is around 1.5, 1.6% with respect to cement. And this value is more or less similar to the value already observed in other researches. The content of CO2 does not modify the average values of flexural strength and pH. I didn't mention before pH, as the absorption is not so large, so pH remains more or less the same. And however, the scatter, so the distribution of the stress, the strength in compression and in flexure with respect to the average value can change when we have the addition of CO2. Sorry. And this is an important aspect, especially for the structural engineers, which define the safety factors that you have to apply for the calculation by considering not only the average value, but also the scatter around this value. So, concluding, CO2 added to cement-based mortars can improve the quality of these mortars. So, as future works, we would like to work to see what happens in different cements. We just used CEM1, but at least in Italy, CEM1 is not on the market now because the impact of this type of cement is too high. So we have to use other types of cements. We would like to extend this analysis also for concrete, not only to mortar. And we would like to add CO2 made with the carbon-13. Why we would like to do this? Because when we add CO2, the CO2 is also present in the atmosphere. So we are not sure that the CO2 is absorbed by the system from the dry ice pellet or directly from the atmosphere. As carbon-30 in the atmosphere does not exist in many of the cases, so this could be considered as a marker. So after testing the material, we can see whether or not this type of carbon is within the system we have created. So we are sure in that case that the CO2 was absorbed by the dry ice pellet. So thank you so much for your attention.
Very nice presentation. So, apologize, I missed part of them. So I didn't capture like how you quantify your the CO2 absorption capacity of that, because you say at the end of the slide you said like it's about like 1.6%, but I just missed part of that, so I just want to figure it out. Yeah.
Sorry. Anyway, so anyway, after testing in compression the paste, we crushed the paste into a powder, and then we measured the content of calcium carbonate within this.
So you're using TGA?
We use a calcimetry.
Oh, okay. All right.
Okay.
Yeah.
And so we consider the situation without CO2 as the reference, and we measure the increment of the content of calcium carbonate with respect to this.
Yeah. I got it. Yeah, that's my question. Yeah, just missed that part, so thank you.
Yeah, you're welcome.
Here.
Very interesting work, It's so nice to see people from different, just perspective, to have this, kind of testing. Yesterday, there's a session for the cementation by carbonation also.
Yeah.
We see some people, they just inject carbon, dioxide, into the mixer. So you are using the pellets of the dry ice. Okay, very interesting. So from your testing results, you see the strength, there isn't that much benefits, but you see the benefits on the, standard deviation. So my question to you is, still in the long run, this kind of research, certainly, just cut down the food, carbon footprint, those kind of things are very good. But still, from application-wise, do you think, what's the potential application for this kind of research? That's my comment.
So at the moment, we cannot obtain a large absorption. So from environmental point of view, yes, we have a benefit, but it's not so much. From a structural point of view, yes, you didn't modify a lot. You cannot modify a lot the strength. But for the structural engineer, it's also important the distribution of the strength around the average value. Okay? So if you reduce this distribution, if you reduce the dispersion of the strength, you can, let's say, use a lower safety factor. So from a structural point of view, an advantage can be achieved. I cannot quantify at the moment how much you can reduce your safety factor anyway. But I think that in future works, maybe we can define it better. Maybe applying this type of concrete also for structures. Also in structures, real structures, maybe. Okay. Thank you.
Very interesting work, thank you. I have a question. You choose to work on 1.6% because the peak of the calcium carbonate. But your compressive strength, the page before, you could go up to 5% without reduction of compression strength. Perhaps some page, you could go to 5%, if I'm not wrong, without reducing your compressive strength of your cubes.
Yeah, the cubes were made with only paste.
Only paste, yes.
Okay.
So my question is, I have two questions. Why don't you try to go more than 1.6 if compressive strength is not reducing? And two, what is the mechanism and the microstructure for which the scatter reduced due to this very small calcium carbonate?
So we cannot, we didn't use more than 1.6% because it was not absorbed, as you can see from the results of the calcination. So it is released in the atmosphere, maybe. So it is not convenient to add it. Why we don't have any, we have the reduction of the scatter? I don't know. At the moment, frankly speaking, I don't know. It is one of the things that we would like to investigate better with the new test that we are going to do. Thank you.